The first thing we're going to be discussing is the concept of a limit. Now, limits are going to be an important topic for us because they're really the foundation of all of calculus. So the first question that we need to consider here is simply, what is a limit? In order to do that, we're going to look at this example. So we've got this function, f of x is equal to x cubed minus 1 all over the quantity x minus 1. And I've gone ahead and sketched out the graph down here. So you'll notice we're basically looking at a quadratic function. We have a little hole right here where our function is undefined. So first thing I want to consider with this is just what's happening to the graph at x equals 1. And as I already pointed out, at x equals 1, we have a hole in our graph. So there's a hole. Okay. Now, for limits, though, the more important question isn't what's happening at x equals 1, but more what's happening to the graph around x equals 1. So in order to figure this out, we're going to consider two things. First, what's happening as our x approaches 1 from the left, and then second, what's happening as x approaches 1 from the right. So let's consider the left first. So we think about this as x is approaching 1 from the left-hand side. You can see that our y value is starting to approach 3. Now from over here, we'll see the same thing. As x is approaching 1 from the right-hand side, our y values are again approaching 3. So what this means for us then is that the limit as x approaches 1 of f of x is equal to 3. All right, so when we have this situation where our function is starting to approach the same value from both sides, whether it exists at that actual point or not, this is what we call a limit. All right, so more generally, we would say that the limit as x approaches c of f of x is equal to L if our y values are approaching L as our x values are approaching c. So let's take this concept of a limit and let's apply it to this next set of examples. All right, so we've got this function here. I've got it graphed out, kind of an interesting piecewise function, and we're going to be looking at some different limits. So first I want to look at the limit as x approaches 0 of f of x. So x approaches 0. We're going to have to look at it from both the left-hand side and the right-hand side. So let's start from the left. We come in as x approaches 0 from the left-hand side. We see that our function is approaching -2. And as x approaches 0 from the right-hand side, same thing, our function is approaching -2. So since it's approaching the same value from both sides, we say that our limit is equal to -2. Again, it doesn't matter that the function has a hole right there. It doesn't matter for limits. The only thing that matters is what's happening around that x value. All right, so next we're looking at the limit as x approaches 2 of f of x. And again, we're going to come in from both the left and the right. So we look at the limit as x approaches 2 from the left-hand side. We can see that our y values are approaching 2. And if we come in, we're approaching 2 from the right-hand side. Our y values are again approaching 2. So our limit in this case is equal to 2. Next, the limit as x approaches -3 of f of x. So let's again start from the left. So as x approaches -3 from the left-hand side, our y's start to approach a +1. But as x approaches -3 from the right-hand side, our y's are approaching 0. So this time, because our y values are approaching something different from the left and from the right, we say that our limit does not exist. And we abbreviate that as DNE. So So again, because we have different values on the left and the right, our limit does not exist. All right, next we're going to look at the limit as x approaches -4 of f of x. Let's again start from the left. As x approaches -4 from the left-hand side, you can see that our function is going down toward -infinity. And as x approaches -4 from the right-hand side, you can see that our function is approaching positive infinity. So once again, our function is approaching two different things from the left and the right. So we have this issue again where our limit does not exist. Lastly, we're looking at the limit as x approaches -5 of f of x. Let's start from the left. As x approaches -5 from the left, our y value is approaching -1. And as f of x approaches -5, or sorry, as x approaches -5 from the right, f of x is approaching -1 again. So the two different sides match, which means our limit is -1. Okay, so that's the basic idea behind finding limits from graphs. We can just follow the curve of the graph, and if both sides match up, then our limit is going to exist. Next, we're going to look at how to find limits looking at an equation instead of looking at a graph. So when we're trying to find the limit from an equation, for now, the way that we're going to do this is kind of using brute force, meaning we're just going to pick some numbers around our c, plug them into the function, make a table, and try and see what's happening from there. Later on in later videos, you guys will see more sophisticated techniques for finding these limits, but for now, we're just going to keep it simple. Okay. So this next one, we're looking at the limit as x approaches 2 of this function x squared minus 3x plus 2 all over the quantity x minus 2. So because we're looking for the limit as x approaches 2, I've gone ahead and put 2 in the middle of my table right here. Now, like I said above, it doesn't matter what's happening at 2 itself, but it matters what's happening around 2. So I went ahead and picked some values really close to 2, both to the left and to the right. So I have 3 values over here to the left of 2 that are just a little bit below it, and 3 values over here to the right of 2 that are just a little bit above it. I went ahead and plugged these in ahead of time so as not to waste your time in the video, and here are my results. I got 0.75, 0.99, 0.999, 2 doesn't matter, 1.001, 1.01, and 1.25. Okay, all right, so now we're going to use this table to try and figure out our limit. Well, if we come in from the left-hand side here, as our x is approaching 2 from the left, we can see that our y values are starting to approach 1. And if we come in from the right, as our x's are approaching 2 from the right-hand side, again, our y values are approaching 1. So since we're approaching the same value on both sides, our limit is equal to 1. Let's look at another example. Okay. All right, this time we're trying to find the limit as x approaches 0 of x divided by the square root of x plus 1 minus 1. So since we're looking at the limit as x approaches 0, I put 0 in the middle of my table. And again, I picked a few values just below 0 and a few values just above 0 that we're now going to plug into this function to try and figure out what's happening. So again, I plugged these in ahead of time, and this is what I got. 1.995, 1.9995, and 1.9999. Doesn't matter what's happening at 0 itself. And then 2.0000, 2.0005, and 2.005. So we can see as x approaches 0 from the left-hand side, our y's are approaching 2. And as x approaches 0 from the right-hand side, our y's are approaching 2. So since it's the same value, our limit is equal to 2. All right, this next one, I want to show you a couple different ways that we can solve it. One, using a table method like we just did above, and a second way of just graphing the function and using the graph to find our limit. All right, so in this case, we're given this piecewise function here. F of x is equal to 1 when x does not equal 2, and f of x is equal to 0 when x equals 2. Let's go ahead and just graph this out. I'm just going to keep it simple here. Okay, something like that. And let's just sketch this. So it's saying that when x is equal to 2, our function is equal to 0. So I have this point right here. But everywhere else, it's equal to 1. So everywhere except for 2, we have a horizontal line at y equals 1, and then at 2 itself, we have this little hole right here, and then our point at 2, 0. All right, so now if we think about our limit, so we're looking for the limit as x approaches 2 of f of x. So if we look at our graph, as x approaches 2 from the left-hand side, our y values are approaching 1. As x approaches 2 from the right-hand side, our y values are approaching 1. Doesn't matter that we have that point there at 2, 0. That doesn't affect our limit. All that matters is what's happening just to the left and the right of that x equals 2 value. So in this case, our limit is equal to 1. Now we could find the same thing if we were to do the table method, because you would see down here that everywhere to the left of 2, our function is equal to 1. Doesn't even matter what's happening at 2 itself. I'm just going to leave that blank. And then everywhere to the right of 2, our function is equal to 1. So as you come in, as x approaches 2 from the left, y is approaching 1. And as x approaches 2 from the right, y is approaching 1. All right, let's consider a couple more examples where our limit does not exist. We looked at a few of these previously at our graph up here. We saw that when the left-hand side and the right-hand side didn't match up, then our limit didn't exist. Let's go ahead and look at a few of these examples from equations. All right, so this one we're looking at the limit as x approaches 0 of the absolute value of x divided by x. So again, I'm looking at x equals 0, so I went ahead and put that in the middle of my table right here. And I'm going to pick a few values to the left of 0, a few values to the right of 0, and plug those into my function. All right, so if you think about this function, absolute value of x divided by x, essentially since the absolute value function just makes everything positive, if we're plugging a negative number into this function, we're always just going to get a -1 because we're dividing a number by itself except the numerator is positive and the denominator is negative. So everything to the left of 0 is a -1. But if we plug in any positive number, we'll just have a number divided by itself, both of which are positive. So those are always just going to be a positive one. So we can see as x approaches 0 from the left-hand side, our y is approaching -1. But as x approaches 0 from the right-hand side, our y is approaching a +1. So because we're getting a different value on both the left and the right-hand side, this is how we know that our limit does not exist. All right, now one more way that we can get a limit that doesn't exist is something like this rational function. So we're looking here at the limit as x approaches 0 of 1 over x squared. So you may remember this function from 171. This is just a rational function with its vertical asymptote at x equals 0 and its horizontal asymptote at y equals 0. And it just has these two different branches in your first and second quadrants, and it looks something like that. Okay, and of course the domain excludes x equals 0 because that would give us a 0 in the denominator. All right, so now if we think about our limit as x is approaching 0, as x approaches 0 from the left-hand side, we can see that our y values are going up to positive infinity. And as x approaches 0 from the right-hand side, we can again see that our y values are approaching positive infinity. Okay, so we're approaching the same thing from both sides. So why am I saying that the limit doesn't exist? The issue here is that the definition of a limit says that our function has to get close to a single number L, okay, meaning it has to actually approach a number. In this case, it's approaching infinity, which isn't technically a number. So anytime your graph is going to positive or negative infinity, that doesn't actually count as a limit. So instead, we would say here that our limit does not exist. Or of course, we can abbreviate that D and E. All right, guys, so that's our introduction to limits. Keep watching the next video if you want to learn about one-sided limits.